How many fans belong in a fan wall?
Total airflow divided by one fan, plus 1 is a useful first check, but it is not yet an N+1 design.
The remaining fans must still deliver the required airflow at the required pressure after one fan becomes unavailable. Let's build a 60,000 cubic meter per hour AHU wall and test it one tile at a time. First, define the availability promise. N is the number of fans required to meet the design duty. N+1 means one additional fan or one fan failure capacity. It does not automatically cover two failed fans, simultaneous maintenance and failure, loss of a common power supply, controller failure, blocked filters, or a closed common damper. Write the required unavailable fan count in every common mode dependency before choosing the array. Our illustrative duty is 60,000 cubic meters per hour at 800 pascals fan static pressure. At that pressure and the selected air density, one candidate fan can deliver 10,000 cubic meters per hour within its permitted speed and power. The first arithmetic is N equals 60,000 divided by 10,000, so 6 operating fans are required. Add 1 for N+1, 7 installed fans. Now test both states. With 7 healthy fans operating together, equal sharing is about 8,571 cubic meters per hour per fan. If one fan is unavailable, 6 remaining fans must each deliver 10,000. That fail fan point, not the comfortable normal point, is the essential curve check. Confirm pressure, speed, electrical input, motor reserve, sound, and stability for both states. Parallel fans add airflow at a common pressure, their pressures do not add. The simple division can still fail. Suppose installation effects, density, tolerance, or the required control limit reduce dependable per fan capacity at 800 pascals to 9,200 cubic meters per hour. 6 remaining fans produce only 55,200 short of the requirement. Recalculate, 60,000 divided by 9,200 rounds up to 7 required fans, add 1, and the wall becomes 8 installed fans. 7 or 8 is therefore an engineering result, not a preferred grid shape. Next, check the fan-out bay. A stopped fan can become a leakage path or spin backward. The design may need a backdraft or isolation device, partitions, and a control sequence that identifies the failed module, isolates it, and redistributes speed without unstable hunting. Include the pressure drop and leakage of those devices in the selected configuration. A blank panel may also be needed where the physical wall has more openings than active modules. Then audit common modes. If all fans share one breaker, one controller, one communication link, one pressure sensor, or one upstream power path, adding a fan does not make those items redundant. Define whether the project needs split power feeds, grouped controllers, independent alarms, sensor voting, local fallback, or fire and smoke overrides. N+1 describes fan capacity, system availability depends on the complete architecture. Also separate maintenance from failure. If the owner must remove one fan for planned service and still survive another failure, that is not a one unavailable fan requirement. It may lead to N+2 capacity or another stated strategy. Likewise, a standby arrangement, one fan normally off, is different from an all-running array in which every healthy fan shares load and the remaining fans speed up after a failure. Name the sequence explicitly. Now fit the arithmetic into real geometry. Check wall width and height, module spacing, access side, lifting path, cable routing, guards, isolation device depth, and downstream clearance. Poor inlet or outlet geometry can change array performance. AMCA's fan array method combines individual contained fan airflow at constant static pressure, but the real module, partitions, controllers, and appurtenances still affect the assembly. This real Longwell fan wall assembly shows why the layout must be treated as equipment, not just a multiplication table. Each module needs a serviceable boundary, consistent airflow approach, secure mounting, power and control connection, and identification. The individual LWBE3G plug fan family is only a candidate until the exact model and the assembled wall are checked at the project duty. Commission both states. Measure total airflow and pressure with all commanded fans available, then run the approved one-fan-unavailable functional test.
Confirm the failed bay isolates correctly, alarms reach the BMS, remaining fans settle at the intended speed, current and power stay within limits, airflow recovers, and vibration or resonance does not appear. Record which fan was unavailable and rotate test duty if the control strategy equalizes operating hours. The final fan wall schedule should state design airflow and pressure, air density, required unavailable fan count, candidate model, quantity installed, normal and fail fan per module points, maximum speed and power, module isolation, control and alarm sequence, common mode architecture, physical grid, service clearance, sound target, and test plan. Send that schedule to Longwell for an array review. N+1 is proven by the fail fan duty point in the system sequence, not by adding one square to a drawing.